I'm Angelo Vermeulen. I'm an artist, biologist, and a space systems researcher. And during my talk, I'm going to try and explain my quite layered practice. I'm actually combining different fields. I'm combining science, engineering, art, and design. And I'm going to illustrate this by talking about two specific projects. The first project I'm going to talk about quite in detail is a biomod project. It's a project in which we build living ecosystems inside computers. It's a community art project that tries to reimagine the relationship between nature and technology. It's a project that has been built all over the world over the past 10 years. The other project I'm going to talk about is dealing with starship design. With a whole team at Delft University of Technology, we're designing new concepts for starships based on ideas coming from biology. We're developing spaceships that actually evolve and grow over time to deal with uncertain futures. I'm hoping that the people listening to my talk will learn much more about things like co-creation and bottom-up design. How do you work together with a group of people with different backgrounds and create complex systems without a predefined plan? On the other hand, I'm also hoping that they will learn more about designing systems that develop themselves to deal with the uncertain futures of these times. Harun Sawatkap. Good morning, everybody. First of all, I want to thank the organizers for inviting me here. It's a wonderful event. It's my first time in Thailand, first time in Bangkok. I'm really impressed by the Design Week, and I'm happy to share my work with you this morning. Ecosystems inside computers, a Mars simulation in Hawaii, starships that are designed according to biological principles. These are some of the things I'm going to talk to you about today. I'm active in many different fields, and these are the fields that today I'm going to show you how I combine all these different fields: art, design, science, and engineering. I'm actually a biologist. This is my very first study. This is how I started. Many years ago, I did a PhD on this particular animal. I researched the deformities of the teeth of larvae of non-biting midges. A very tiny subject, typical for science, right? You focus on something very small and then you elaborate it. I was looking at the world through a microscope. You might wonder, why would somebody look at the teeth of insect larvae and look at deformities of those teeth? That doesn't make any sense. Well, the thing is, these larvae, they live in sediments of streams and rivers and ponds. And when they're contaminated, the teeth start to deform. So you can actually use those deformities as a bioindicator of environmental pollution. So it does make a bit of sense. But nevertheless, I was really wondering whether I was going to spend the rest of my life looking at the world through a microscope. And I knew I wasn't. I've always been interested in many different things. I've always been interested in art and science. And when I was doing this research, I actually went to art school. I went in the evening to an art school, and I became a photographer. So I was both a biologist and a photographer at a certain point. Now, because I was doing photography and I got exposed to the arts, I got really interested. When I finished all my studies, I got really interested in the arts. And I decided I wanted to be a full-time artist. And I started creating art in which I embedded and used my background as a biologist. And I created bioart, biological art using biological organisms. These are a few examples. On the left-hand side, you can see an artwork that is actually using Darwinian evolution. On the right-hand side, there is a project in which we used biological organisms as non-human agents to disrupt data. Things like this, different kinds of experiments. There's one particular artwork that I'm going to talk to you about in big detail, and it's called Biomod. Biomod is a project in which we use e-waste, electronic waste, old computers that people throw away. We take them apart, we check the components that still work, and we build functioning computer units with those parts. We put those computer units together in a sculptural network, and then crucially, we built living ecosystems inside of the computers that use the waste heat of the electronics to grow and develop. This was the very first version we developed. In 2007, I was an artist in residence at the Aesthetic Technologies Lab in Ohio. And as you see a 2-meter tall case. Whoops. A 2-meter tall case, a network of recycled computers, about 5 computers, and a whole ecosystem of plants living inside of that. One of the interesting ways in which we connect waste heat and biological life is by using this particular system. On the right hand, on the top, you can see water cooling. It's a computer being cooled instead of a little fan, it's being cooled using a coolant liquid. But instead of using a toxic commercial coolant liquid, we're using a culture of single-celled algae. We're actually cooling electronics using living biology. The algae benefit from the computer because they heat up and they grow better. And the computer, of course, benefits from the algae because it's being cooled. So it's a symbiosis between computers and single-celled algae. And it's this kind of imagination that is very interesting. It kind of shifts your perspective on how technology and biology relate to each other. And I think that's at the heart of this project. Later on, we kind of developed the concept of biology and technology working with each other. And instead of the computers only passively taking care of the ecosystem through exchanging heat, we also started working with sensors and robotics. And this is one of the robotic systems that we developed. We recycle as much as we can. The whole artwork is using a lot of recycled materials. The same thing here. This was an old toy, like a car, remote-operated car. We hacked it. We connected it to the network running on the computers. And then the computers could position the car above a specific plant, and they could squeeze a wet sponge above a plant. So you could actually see how the computer was trying to take care of the different plants in that ecosystem. We also, for example, this is a version that we developed in New York City, we started experimenting with the ecosystem itself, and here, for example, we're actually growing vegetables inside the computers that during the project we harvested and then ate. One important component, one important design component of this particular project is the fact that in this project, for the first time, I started working differently as an artist. Normally, artists, they make their own work in their studio, sometimes assisted by a group of people, assistants, and then they bring the work to the museum or the gallery. I decided to work a little differently, and I decided to start exploring the concept of co-creation, creating an artwork together with people. And so what you can see here is one of the last versions of the project that we developed in Taiwan, in the National Taiwan Museum of Fine Arts, and here we worked with 100 people. And what is typically for the way we work is we work without a plan. There is no plan. We come together, I explain the concept, basically the way I explained it to you now, and then we start. And every day, we just figure things out. We add a few things, we remove a few things, and gradually over time, the artwork emerges out of those interactions. It's quite challenging, because when people come in, they expect instructions, but there are no instructions. People are free to add and to remove whatever they feel like. And of course, there is dialogue and there is discussion, but there is no, how to put it, there is no central blueprint. It's a very different way of designing things. It's bottom-up design. That's the way you could call it. Instead of top-down design, bottom-up design. This was the result of the project in Taiwan, a beautiful large-scale art piece. What you can see is a greenhouse in front that actually captures the heat of the electronics and is used to boost the growth of different tropical plants. You can also see terminals on the floor where people can lie down and they can look at a screen above their head, and that's how they access the network. There are different computer games running on that network. And then in the back, there is actually a window farm that is developed over the windows of the museum that is also connected to the installation. And mind you, this is a complex system. There are different interactions going on. It all works, and it has been built through daily interactions between people without a central blueprint. I'll show you a video now which gives you a few testimonies of some of the participants in this Thai project. The video, please.
普通高中，然后念一般综合大学的，然后没有机会接触到，比如说设计的人才，或是其他比较对我来说非常需要技术的东西。然后就是来这边认识很多人，然后能够跟他们学习一些平常不会接触到的东西，就是收获还蛮多。然后整个团队计划，整个团队工作，整个团队一起进行别人已经进行到一半的工作，我觉得这是就是蛮酷的经验。对。然后我们就是公斤湖，它是一个中国的形状跟一个台湾的形状，所以这一瓶是从台湾的尺寸来。
地方是人其实来来去去的，然后你就会发现说你要怎么样去跟一个人互动，然后开始主动逼自己主动去了解现在发生什么事情，然后打破一个像局外人的情况，会觉得还蛮有就是突破吧，对吧？因为就是你要怎么样跟陌生人一起合作，然后一起做同样的事情，然后就发现说，做电脑的人跟你想的完全不一样，他可能就一直想他的极限不同啊，他的口红啊。可是做设计的人就会觉得，这个就不美，或是这个地方很奇怪，不美，然后不均衡的，所以就会觉得原来就跟生活的世界跟剧场世界完全不一样。
我觉得很不一样，因为自己在做的时候是你自己想做什么，其实不太会有人干涉你。但是跟别人一起做的时候，有时候有让步啊，然后有时候有妥协，然后有时候你要有坚持己见的时候，所以我觉得跟自己在做作品是差很多。我觉得是一个反思吧，就是我们制造了很多，我们可能透过消费或生活上，然后制造了很多不要的东西。但其实这些东西是可以再利用，然后跟可能环境做一个结合。虽然它不是一个很完美的系统，但它是一个它是一个有功能的系统。
所以 biomod 的计划其实里面蕴含了非常多的不同的循环系统，那整个循环系统形成一个生态。那这个biomod 计划呢，其实永远是一个未完成式，因为它是一个社群的模式，社群需要有序经营下去，才可以看到它的最后的成果发酵，甚至是社群会不会有一个结束的 ending 都不知道。那这个计划虽然在国美馆只展出2个月，但其实它是一个开始。它之后可能这个装置不存在，但是它的整个创作过程或者是整个精神，相信都会留在所有的创作者的脑海里面，或者是留在所有参观者的体验当中。
So, one important thing that you could see in the video is that I'm always actively seeking to build mixed groups, mixed communities. Different disciplines, people with different age, different cultures, put them together and then start working together. Of course, this requires a particular attitude. And that's where the concept of co-creation comes in. I've already talked about bottom-up design, where you design without a central blueprint. Co-creation is something a little different. The concept of co-creation actually means that you step into another field, even though you're not a specialist, but you're not shy about it. You're open to learn, and the beautiful thing is when people step into a field that they don't really know, it might actually be an advantage not to know so much about it, because you have a different perspective. So when you're building computers out of e-wastes, not everybody that does that needs to be a computer specialist. It's quite interesting to have a mixed group of people working on that. This often leads to new ideas and innovation. When we're working with this project, and you're actually bringing the same concept to different locations throughout the world, in every single instance, the actual result will reflect the local culture. That's actually what we're really interested in with this project. And this, for example, was a version of Biomod that we built in the Philippines. And I will explain to you how over there it got its own local interpretation. What you can see on the slide is Maria Mikiling, the little image there. In the Philippines, there is still a lot of spirits that represent specific mountains. She's the spirit of Mount Mikiling. And the interesting thing about the mythology of Maria Mikiling is that most of her stories are about people not respecting nature, not respecting the ecology of the mountain. Now the thing is, we were actually developing Biomod at the foot of this mountain. So we're developing an ecologically inspired artwork at the foot of a mountain full of ecological mythologies. So of course it made perfect sense to connect both. And so we started developing Biomod inspired by these mythologies. And we worked together both with local Filipino game designers, but also with local Filipino woodcarvers. They all contributed to the artwork and the result you can see on the left-hand side. Now, there is a bit of a problem with this project in the tropics. Remember, I talked about how in Biomod we're recycling waste heat to grow internal ecosystems inside computers. But what are you going to do in the tropics? It's already so hot. Why would you use the heat of electronics to grow plants? That doesn't make any sense. So we had to rethink the concept. And this is the solution the Filipino team members came up with. We're using aquaponics. In aquaponics, you're actually growing plants without soil. You're basically dripping water over the roots of the plants. And you're using the water of fish tanks. I mean, it's an old traditional technique that was used many years ago, I think even thousands of years ago, in Asia. And so the way we use it is the following. We're still using the algae to cool the computers. Remember the culture of single-celled algae? Of course, the algae get warm. And then we pump the warm algae through a submerged spiral inside a fish tank. So the more people use the computer, the more the algae heat up, and the more the fish tank heats up. And the more the water of a fish tank heats up, the more the metabolism of the fish goes up, and the fish produce more nutrients for the plants. So that's the kind of cascade that we built throughout the system. So we kind of found a solution for this problem using the waste heat. And this is how the project keeps evolving over time. It's really an artwork that keeps reshaping and redefining itself over time. Now, when you're working as a Western person, as a white male person, in countries like the Philippines that have been colonized before, it doesn't come without friction, of course. And it's a very delicate balance of being an outsider and coming into these countries and creating with the people there. I've written this paper together with my Filipino counterpart, Diego Maranan, which is specifically exploring these issues. So anybody who's interested in how East and West can collaborate and the kind of interesting issues that arise from that, you can download this paper for free from the internet. So as I said, it's an evolving artwork. These are all the versions that have been built so far, but we've also stimulated the development of this artwork by open sourcing it. So basically it's an artwork that many people, anybody can build, use the name, they use the concept, and they can keep on developing it. Now, I kept on working with the same people over and over again, and at a certain point I decided to launch a collective. So I'm now part of a collective. I'm not working as an individual artist any longer. Our name is Space Ecology's Art and Design Seed. We're a collective representing people from different places all over the world, as you can see here, doing different things in many different places. So what are some of the conclusions of this first part of my talk? Well, first of all, if you want to stimulate creativity, if you want to make a project like this successful, a project in which you want to use bottom-up design and co-creation, you need diversity. You need to actively seek out diversity. You need to look for people that are very different, bring them together, and make them work together. This will lead to really novel ideas. It's the wisdom of the crowds, basically. It's the wisdom of many different perspectives. It's very important. The second thing is you have to avoid that hierarchies start building themselves. Wait a second. Yes. You have to be careful with hierarchies establishing themselves within such a project. You have to be careful how to put it. You have to make sure that everybody stays equal in the group. It's very tricky because sometimes people start to take over a project, and that's something you want to avoid, unless their leadership is a natural leadership. When people naturally have a lot of knowledge about a particular topic, people within the group will gravitate towards them, will start learning from them, but it has to stay a natural process. And that's something I think you need to guard. So when you're working like this, when you're doing co-creation, you're all working together in a more horizontal way, there is still some sort of leadership that you need. You need some sort of facilitating leadership. Somebody needs to guard the process. That's definitely important. Autonomy, also very important. You need to allow people to develop their own things. I must say, for some people, it's very uncomfortable to walk into a project and not get instructions, to just be autonomous to do something. In the beginning, it can be a little awkward, but once you get over it, it's actually very empowering. And then the last thing that is very crucial in projects like this is to keep the communication flow going. And that's the role of the facilitating leader to make sure that the project is successful, is to make sure that everybody keeps communicating. So these projects, like the one that I just explained to you, so led me to a few new things in my life. This was, I didn't calculate this. This just came along my path. So what happened is I started in biology, I started making bio art, and then these new things opened up for me. And I'm going to briefly introduce these different things. The first one is bio-inspired architecture. I basically started collaborating with an architecture office in Vienna. They invited me to work with them, and we started to work on architecture from a biological perspective. And what you can see here are different aspects, different examples of how you can blend architecture and biology. On the left-hand side, you can see mycelium. It's basically mushrooms that are digesting cellulose waste, and then the resulting material you can dry and you can use as a building material. In the middle, you can see a robot, a 3D printing robot that prints with calcium carbonate, a natural material, and the robot is also using biologically inspired algorithms. And on the right-hand side, you can see a slime mold. The slime mold is a primitive organism with a specific intelligence. It's very good at building networks. And we used its networking building capacities to develop architecture, to solve architectural problems. So these are different examples of how you can use biology in architecture. We also have a book with all the results about it, so if you want to learn more about this. Because of those projects, I also got invited by the European Space Agency, by a particular research group at the European Space Agency. It's called Melissa. And this research group at the European Space Agency is actually developing circular ecosystems, regenerative ecosystems. These are ecosystems that take all the waste that comes out of a human body and then using bioreactors gradually breaks it down and turns those molecules into nutrients for plants, and then the plants produce food and oxygen for the astronauts again. So it's a fully closed system. It's actually being developed for long-term space exploration, so people can survive for a very long time in deep space without having to rely on Earth, right? I thought, the first time when I heard about this, I thought it was fantastic. It's a really interesting concept. It's very sustainable. It can also be used on Earth, so I was very happy to join them. And in the beginning, I basically worked with them as an artist. I made a few artworks inspired by their system. This is an artwork, an installation art piece, in which there was also one of their bioreactor was part of the artwork. And then the last thing that I wanted to introduce is I got interested in space settlement, living in space. And this is the High Seas mission. The High Seas program is a NASA-funded program that specifically investigates the effects of long-term isolation of small crews working in a Mars-like environment. What happens to the group dynamics when you lock up people in a small space and you make them work together? High Seas is a Mars habitat. It's built at the flank, on the flank of the Mauna Loa volcano in Hawaii. It's the largest volcano on Earth. The landscape on the Big Island in Hawaii is very much like Mars. The soil is more than 90% similar to Martian soil, so it's an ideal, isolated environment to practice living on Mars. I was part of the very first mission back in 2013. Right now, there have been 5 isolation missions. I have been living in that dome together with 5 other people for 4 months, locked up in that space. We had contact with the outside world through email, but the email was delayed, because if you're living on Mars, your email would also be delayed. So we didn't have any SMS, no phone calls. And as you can see, we did all kinds of scientific research. We were allowed to go outside. This is called an EVA, an extravehicular activity. And then you have to wear a spacesuit. It's not a real spacesuit, it's more like a spacesuit simulator. And what the suit does is it isolates you from the outside world. It isolates you from the outside world to make sure you don't get any direct fresh air. And also it inhibits your movement. It makes it a bit more difficult to move around and to take soil samples. That's the function of that spacesuit. And of course, we also had parties. It's not like you're always working when you're living in isolation. This is a birthday party, you can see there down below. It's part of daily life in a mission like this. One of our basically our main scientific study during this experience was a food study. We were actually tasked to research the future of food in space. When people think about astronaut food, they often think about what you can see on the left, a tube or pills. Those were the early days of space exploration, when they really thought this would be the solution to feed astronauts. A tube is very efficient, it's very compact, you don't need any equipment, so it sounds like the perfect solution. The problem is, the astronauts hated it. You can't keep feeding people with tubes. I mean, psychologically, it just doesn't work. We're only human, and part of our humanity is food culture. I mean, in a country with such incredible food culture, that's like pretty obvious. On the right-hand side, you can see the current food. That's food, how it's served at the International Space Station. It's much better. It might look a little pre-packaged and everything. It's much better. It's not bad at all, but still. There is a psychological phenomenon which is called menu fatigue. People get tired of eating the same pre-prepared foods over and over again. Quite logical. So one of the potential solutions is to allow astronauts to cook once they're on the moon or once they're on Mars. What would happen? And so we were asked to experiment with this. We were basically the first crew in the history of space exploration to try out cooking ourselves. So we got a whole bunch of shelf-stable ingredients at the start of the mission. These are ingredients you don't have to cool. These could be traditional ingredients like rice and flour and honey, seaweed and tofu, things that you don't need to cool. And then we were allowed to improvise meals with this. The interesting thing is that the experiment was set up like this. We had to eat 2 days of astronaut food and then 2 days of cooking. 2 days of astronaut food, 2 days of cooking, the whole mission. And with the cooking, we didn't get any instructions. We were allowed to do whatever we wanted to do. And of course, this was the interest of the researchers. They wanted to see which kind of food pattern would evolve over time when you would run an experiment like this. But you have to imagine, this is science. So for every scoop that we put on a plate, we had to weigh it, we had to film it, we had to evaluate it on a sheet of paper, and then after we ate it, we had to evaluate it again. So the first time you get out of a mission like this and you have breakfast without paperwork, it's fantastic, of course. These are some of the things that some of my crew members improvised. I must say, some of my crew members were genius in improvising food with these shelf-stable ingredients. They were very talented. I was just mediocre. I was not so gifted in cooking all these beautiful things, but some of the things were quite spectacular. What are some of the lessons that I learned in this mission? Well, the first one is that food has a huge impact on many different levels in such conditions. First of all, we decided to make sure that every day 2 people would be responsible for cooking, which means that those 2 people would be in the kitchen a lot of the time during that day. And what happens if people are together in the kitchen? They start talking. It's very important. If you live together like this, you need to keep communicating. You want people to share different things. Also, being allowed to improvise was a great outlet for creativity. And I can tell you, if you live in a small space like this, locked up, you seek creativity. You seek possibilities to do something new. Because after some time, you know every square inch of the habitat. And then, thirdly, when you make food for other people, It's a very human gesture, of course. And then sharing that food and getting feedback has a huge psychological impact on the group dynamics. So there's all these very interesting dynamics of introducing cooking in space exploration. The other topics that I'm listing here are similar to the things that I just talked about when I was talking about biomod. It's the importance of diversity. We had quite a diverse crew. As you could see, we were with 3 men, 3 women. But even within the cultural diversity, there was quite an interesting mix. There was somebody from Puerto Rico, African American, Russian American. I was European. I'm still European. There was a Canadian. See, and this kind of multicultural mix generated very interesting conversations, but also we had different backgrounds, different professional backgrounds, which made for interesting problem-solving skills. You know, when we had a problem, we had so many different approaches, so many different perspectives that we mostly figured it out by ourselves. Autonomy is another important one here. If you want to send astronauts to deep space, for example, you want to send them to Mars, it's going to take quite a while. Going to Mars and back home is at least 2.5 years. Right now, astronauts in the International Space Station are constantly monitored. They're basically operators. They have no autonomy. They have to listen to instructions all the time. Carry out this experiment, now you have to do this experiment, do this, do this, do this. A friend of mine, a researcher in the field of space exploration, she's a space psychologist, showed me some of the instructions that the astronauts get. And to introduce a USB stick in a laptop at the International Space Station is like 1/3 of a page of instructions. So that's how detailed the astronauts are being guided. Sometimes just too much. It's too much bureaucracy, of course. So if you go into deep space, there is no more real-time contact. You can't immediately talk with them anymore. So you need to develop a different culture. You need to start trusting your astronauts instead of trying to control every single moment, right? So that's where the autonomy comes in. And it also refers back to the original project I talked about to biomod. If you're an artist and you want to collaborate with people and you want to give them input in the project, you cannot be a control freak. It's not going to work. If you're a designer and you're working with a community and you want to work with them, you want to design with the community, for the community, you have to trust them. If you start micromanaging everything, people will be like, hey, this is a joke. You know, you're telling us we can collaborate, but actually we just have to listen to your ideas, right? This is really crucial in many different fields. The last one here is communication. Communication is really crucial. The thing is, different leaders have different leadership styles. That's something I discovered during this mission. I learned most about leadership, to be honest, because, oh, I didn't tell you. I was actually the commander of this mission. I was in charge of the mission. Well, in charge. The thing is, you, as a commander, you have the responsibility to keep people together. And there are different ways to do that. My approach was making sure that people keep communicating. The nightmare scenario that I had in mind was, and these are stories that I heard about stations in polar regions, where scientists lock themselves up in their own room. They only quickly come out to the kitchen, grab some food, and disappear in their room again. I was like, I don't want to live like this. That's horrible. I really want people to be together. Also, when you're together and you communicate, when there is a problem, you know how to handle the problem because you're constantly aware of each other's capacities and skills. If you're all individuals, never communicating, there's a problem, it's going to be very difficult to come together to solve that problem. So there are many reasons why you want good communication in a group like this. This brings me to the last part of my presentation, actually the research that I'm currently doing. After this experience for NASA, I started thinking about the next step. It was like, what's beyond Mars? I'm always thinking about the next step. It's my nature, I guess. And I got really interested in interstellar space. Interstellar space is basically the space between different stars. How could the future of humanity look like when we're traveling not just within the solar system, but we're traveling to the next star? The nearest star is about 4 light years. It's actually, we can reach that. Yesterday I was talking with some of the other speakers and somebody was talking about intergalactic travel. This is not intergalactic travel. The distance between galaxies is way too big. But the distance between stars, you know, we will handle that. So if you want to design for this, if you want to design for this future, there is one crucial defining element, which is actually a beautiful metaphor for the times we live in. What is typifying for interstellar space is that you're dealing with uncertain futures. You have no idea what's going to come up. If you're going, remember when, well, not all of you might remember, but when the Americans were going to the moon, they wouldn't go to the moon in one step, taking all the risk. They would go closer and then come back to Earth. They would learn, they would adjust their system, they would understand the risks and the dangers a bit better, then they would go a little further, come back to Earth. And gradually, they would go closer and closer. This is how you develop a safe system. When you're traveling interstellar, this is impossible. It's too far. You can't be, hey, let's go a little bit interstellar and then go all the way back to Earth to solve the problems and go back. No, that's just totally impossible. So we are in a paradox. How do you design solutions for a future you have no idea about? How would you do that? That seems like impossible, right? From a traditional engineering perspective. Well, the thing is, biology can help. And I'm glad I'm a biologist, because in this way, I can think a little deeper about this. One solution is exemplified by this particular project. It's the only project we currently have that is developing a system to explore different stars. It's called Breakthrough Starshot. It was announced in April 2016. And the concept is like this. They want to send very small space probes, miniature space probes, with a light sail. So basically the probe goes into space, it deploys a light sail, and then with a powerful laser from Earth, you shine the laser, you direct the laser on the sail and propel the spacecraft into space. The thing is, you can actually propel things using light. Light photons propel things. The force is very small, but if you use a powerful laser, you can actually reach a very high speed. With this project, they want to reach the nearest star, the one I talked about before, 4 light years away from here. It's the Proxima Centauri system. If you reach a speed of 10% of the speed of light, you can reach that system in 40 years, which is not too bad. That's a pretty realistic approach. The thing is, the way they deal with these uncertain futures that I just talked about is they want to send between 1,000 and 2,000 probes, a typical strategy from nature. When flowers send their seeds in the air, when fish are reproducing, you see so many of them, and you know that only a few of them will survive. There's a typical strategy to deal with a future that you really don't know 100% what's going to happen. Another approach you can find in this example. This project is called FoamBot. It's a robotic system that was developed a couple of years ago at the University of Pennsylvania. It's a very interesting robotic system. It's not very pretty, but conceptually it's incredibly interesting. It's a robot without a body. It's actually a system, you can see on the top, a basic system, a core module. And if you show a physical challenge to the robot, if you expose the robot to a particular physical challenge, it will calculate the body it needs to overcome that physical challenge. It will then distribute electronic joints on the floor according to that body, and it will start building the body by using polyurethane foam, self-hardening foam. It actually builds the body. It will then calculate a software module, program a software module by itself to operate the body, and it will then tackle the particular physical challenge. I was really mind-blown when I heard about this. This is beyond polymorphic robotics. A polymorphic robot is a robot that has a couple of configurations. Transformers, right? Has a couple of a car and a robot and a few configurations. This has endless configurations because it's like a biologically inspired robot. And this is where I saw the solution for starship design, to design spaceships that can take us to different stars. Why don't we design starships, spaceships, that actually grow and evolve during their journey? And because of the growth and evolution, they can constantly adapt themselves to different conditions in space. And that's what I set out to do, and this is what I'm currently working on at Delft University of Technology in the Netherlands. And this is how it all connects. Remember how I started in biology, became a bioartist, I'm still a bioartist, did all these other different things, and it kind of all converged in this new idea of developing bio-inspired space systems. Mind you, I never consciously planned this. I live by the principle of serendipity. Whatever happens in my life, whatever I encounter, intuitively I feel this seems interesting, I follow. I follow a path. And only in retrospect, when I analyze what's been happening, I come up with these diagrams. It's a very different approach. Once again, I set up a community. I can't help myself. I'm a community builder. In Biomod, I work with communities. For NASA, I worked with a community. Here, I work with a community. I love to work with people. More minds, more disciplines, more perspectives creates better solutions. And so you can see all these different people with different backgrounds. We're called D-Start. That's the name of our team. Now, you might wonder, okay, fine. A growing and evolving starship. How are you going to do that? How would that work? Well, there's something interesting, 3D printing. Something that could change things in space. We can start building infrastructure in space using that technology. Instead of building things on Earth and then shipping them or launching them into space, which is very inexpensive, you can actually start building things inside space. This is a conceptual research project supported by NASA to develop 3D printers that can print trusses inside space, but we could also use it for our project. Now the thing is, if you design a starship that can actually print itself, you need something to print with. You need material to print with. The thing is, when we're traveling at high speeds, 10% of the speed of light, or maybe even higher, these are relativistic speeds. It's not like you can brake, stop, look around, and see if you can find some materials to use, and then depart again. That's not happening. So basically, when you start your journey, you need all the printing material right from the start. You need to have it on board right from the start. It's a bit like what you can see here, the development of an egg, where you start out with the yolk, it's the undefined raw material, and over time it develops into this complex system, which is the chick that comes out of it. It's all self-contained, and so that's how we conceive of our space systems. This is the most abstract representation of what we're trying to do. You can see we have an active, this is actually a representation of our spaceship, of our starship. We have a traditional active component, which is responding to different changes. It's regulating itself. But there's also a passive component of passive materials, raw materials that can be used to bootstrap growth and evolution. What kind of materials would we use? Well, we got interested in asteroids. Asteroids are a beautiful resource of materials. They contain a lot of water ice, they contain carbon, they contain different kinds of metals. They're already out there. You don't need to ship all those materials from Earth, you can just use an asteroid. And so we are designing asteroid starships. An asteroid starship is a concept that has been explored before. It started somewhere in the 60s. The first idea is to transform an entire asteroid into a spaceship. And also in science fiction, there's been a few examples of people writing about this. The difference is in our project, we're doing the math. We're actually building a computer simulation that simulates the whole process of how such a starship would grow and evolve over time. Now, if you want to have a space architecture that actually grows over time, that actually evolves over time, how would that work? Would you have like one big structure, and then if you want to expand it, would you like cut it open and grow it, like what we do on Earth? When you have a building and you want to make it bigger, you can remove a wall and make a space bigger. But that doesn't work in space because it's vacuum, it's way too dangerous. So modular architecture is a really elegant solution to allow architecture to gradually grow and develop over time. And there are many examples in the history of architecture that have been exploring this. This is the very famous metabolist movement from Japan that was one of the early pioneers in this concept of growing architecture using a modular approach. And so in order to make our system work, we started to work with particular module types. We started defining different types of modules we needed to put together to develop such a space architecture. Also, we got interested in a very particular geometric architecture. It's what you can see there on the left is a truncated octahedron. I'm not sure if the translators can translate this perfectly well right now. A truncated octahedron. And the beautiful thing about a truncated octahedron is, first of all, you can nicely stack them without losing any space. Secondly, they have multiple sides. So remember, in space there is no gravity. If you have a space with multiple sides, you can connect one space with many different other spaces. It's really an advantage. And the last interesting aspect of this geometry is that it's a very beautiful geometry. It's a beautiful shape. It's a very balanced shape. So there are all kinds of interesting aspects about this geometry. Like I said, we're embracing the concept of 3D printing in space. So we could imagine, for example, I mean, this is more like a visualization, artist impression. We could imagine mobile robots printing these modules in space and develop the Starship over time. Also, we would be mining the asteroid to print. Because I don't think I made that very clear yet. We're actually, during the journey, we're gradually mining the asteroid, we're extracting materials from the asteroid, and we're using those materials to print the spaceship. So we're gradually hollowing out the asteroid and then developing architecture inside the asteroid and outside the asteroid. The thing is, the asteroid also has an interesting function as a shield. Because if you're traveling at a very high speed in space, at a relativistic speed, tiny particles cause enormous explosions. You don't want your Starship to explode because of some stupid dust particles. So the asteroid kind of helps to counter that. This is how the first visualizations look like. You have an asteroid. The ring is an abstracted propulsion system. We're not focusing on propulsion. We're really focusing on architecture, on biological-inspired architecture and spacecraft design. And you see all these different modules that organically grew like a tail out of the asteroid that has been mined. You can see, it's a little more clear on the screen in front of me, but you can see the modules have different shades, different colors. And that's because we're using differential 3D manufacturing. Depending on the material that is available, because there is a scarcity of materials, it's not like you can find everything on that asteroid. Depending on the availability of the material, these architecture modules will be built out of different materials. One time they might be built out of copper foam, the other time out of aluminum, then out of carbon, and you get all these different elements put together. Here you can see a close-up of different modules. The symbols you see debossed inside the modules are actually indicating functions of the modules. Because remember, we're not building a real Starship, we're building a computer simulation. This is conceptual design, and this helps us to keep track of the different functions that are developing themselves within the computer simulation. Now, I'm a biologist. I always think about biology in many different ways. And for me, it made perfect sense that if we were to build a simulation of a Starship that develops itself through space, we would also have to embed an actual ecosystem inside of it. An ecosystem that would recycle all the waste, that would generate food and oxygen. And so I ended up using that concept that I talked about before from the European Space Agency inside that Starship design. So we're actually embedding an actual research program from the European Space Agency in our conceptual design. And we're turning it into, we're making it part of our computer simulation. So this is the summary of what I've said so far. We have an asteroid, there's resources. You can use the resources to grow your regenerative ecosystem. And when the ecosystem is growing, it actually will give a signal to the architecture to expand itself. And that's how the whole system evolves. Now, when we're traveling through space, through deep space, there are two main challenges. The first one is radiation. There are dangerous radiation events that could kill biology, could kill astronauts. And the second one is particle collisions. I already talked about this before. Small particles can cause huge collisions in deep space. So we need to talk about evolution here. Remember, I was talking about growing and evolving starships. So far, I've actually only talked about growth, about a starship that is printing itself and getting bigger and bigger. But there is something else. Growth is a bit like a crystal that slowly grows itself. Evolution is an entirely different thing. Evolution is changing a shape, changing a basic morphology, like you can see on the right-hand side. And the beautiful thing about modular architecture is you can shift around those modules and you can change the overall morphology of your starship. And so that's something we're also interested in. And so summarized, what you can see here is the starship can actually anticipate what's coming up. It can sense the future, the near future, and whether when the future is quite similar, it'll just grow. it'll just continue to do what it's doing because it works. If the future is very different, it will actually evolve itself, right? It will actually transform its own configuration into a more optimal configuration to deal with that upcoming challenge. And this is the kind of experiments that we're designing. This is the first experiment that we've planned for the next few weeks. We design a space journey virtually inside the computer, a 100-year journey with different events, radiation coming in, different particles, and then we launch a spaceship attached to an asteroid with a particular chemical composition. We launch it, and then we sit back. And then you can see the space architecture slowly, virtually developing itself over time. The interesting thing in this experiment is we're going to experiment with different chemical compositions, asteroids with different chemicals, and then to see in which situations it actually works and in which situation it totally fails. And this is the kind of the goal of our research. So summarized, you can see how I made a big journey from looking at the world through a microscope, looking at teeth from larvae, to building starship concepts. And I'm doing this through basically two big approaches. First of all, I'm embracing multidisciplinarity. There's nothing wrong with being interested in many different things. There's nothing wrong with being interested in one single thing. That's perfectly fine too. And the second big lesson is working with people. You can only do these transitions, you can only build these big ideas by working with people and joining forces and listening to people and creating these kind of novel ideas. We've been exhibiting our research in art exhibitions. It is an interesting evolution that happened. It is basically a kind of the conclusion of my presentation here. We started getting invitations from arts institutions to exhibit our scientific research. This is a supercomputer that we're building. It's a cluster computer, and it's actually a combination of small computers, and if you combine them, you have a very powerful machine. And so now, basically when I go home tomorrow, I have an exhibition opening up in 2 days, so really have a lot of work after this talk. And we're actually exhibiting both the visualizations and the cluster computer. And so without me planning this, my scientific research became art again. And so, like I said before, I'm following the flow, and I'm just being guided by these interests and by art and science. And sometimes they go in very unexpected directions. And I think it's really crucial that when you do this kind of work, you open yourself up to the unexpected, because otherwise you would never move forward. Thank you so much.
Thank you so much, Angelo. Very inspiring and mind-blowing. So now is a Q&A. Please stay on the stage for a few more minutes. We can start by taking questions from the floor. ตอนนี้เป็นช่วง Q&A นะคะ เราอาจจะเริ่มจากถามคำถามจากผู้ชมจากฟลอร์เลยก็ได้ค่ะ ถ้ามีใครมีคำถามที่ยังไม่ได้พิมพ์เนี่ยสามารถจะยกมือถามได้ก่อนเลยนะคะยกมือสูงๆนะคะแล้วเดี๋ยวจะให้เจ้าหน้าที่เอาไมโครโฟนไปให้ยังไม่มีนะคะงั้นเดี๋ยวเอาคำถามจาก Do you think this biomechanics practice can solve real life everyday environmental problems?
There was a question there, I think.
เดี๋ยวตอบคำถามนี้แล้วเดี๋ยวเอาคำถามจากฟลอร์คำถามนั้นเป็นคำถามต่อไปนะคะคุณคิดว่าระบบ biomechanics ที่ได้เล่าให้ฟังในเลคเชอร์นี้สามารถที่จะแก้ปัญหาสิ่งแวดล้อมปัจจุบันได้ไหมนะคะ
Yeah, I'll answer this question in front of me here and there. So bio-inspired practice can definitely solve a lot of problems. It's actually a new approach in engineering. It's called morphogenetic engineering. For anybody who's interested in this, you can Google it, morphogenetic engineering. And it's an engineering practice in which systems are not designed using a blueprint, but you design the basic components and the rules, and then those components, using those rules, design the solution. A very good example of this, because for some people it's still quite abstract, is termites. You know the small insects, termites? They build termite mounds. They're actually very complex architecture. they regulate the atmosphere to an incredible degree. They manage to combine bringing in fresh air but keeping the heat out, which is quite a challenge, and they solved it. Now the thing is, when they built a termite mound, you don't have the star architect of the termites running around with his plan telling every termite what needs to be done. It doesn't exist, right? All the termites have certain rules they use to behave, and out of that interaction comes the solution. And the beautiful thing is that in this approach, when you solve problems like this, because it's a gradual system, you can constantly work or respond to problems that arise during the process. So you can constantly optimize the system. It's a very flexible way of finding an optimized solution. So yes, I do believe that a bio-inspired approach can solve those problems, yes.
คำถามต่อไปจากผู้ชมด้านหลังเลยค่ะ
I had a very similar question. I was wondering if your work with with NASA, especially on how to build the ecosystems into the spaceships, if that was something that you could use in looking at cities and dealing with waste to make them more sustainable.
Yes, there is actually a spin-off company, and I'm part of the spin-off company, which is called IP Star, and that company is specifically doing this. It is trying to translate that technology back to Earth. Indeed, there is, for example, a good example is they're using that technology in a station in Antarctica, in which the waste is digested by bacteria. And basically what happens is, this is quite interesting. In the winter, all the people have to leave the station because it's too cold. And the solar energy that is captured by the station is used to keep the bacteria alive. So the station is keeping itself alive, it's keeping its own ecosystem alive. So that's just one extreme example of using the same concepts back on Earth. But yes, indeed, it's absolutely interesting.
Thank you.
คำถามต่อไปนะคะจาก Q&A ออนไลน์นะคะหรือมีคำถามจากฟลอร์ไหมคะเดี๋ยวถามคำถามจากฟลอร์ก็ได้ค่ะทางด้านหน้านะคะตรงกลางค่ะแถวที่3
Oh, another online question.
Hi. You mentioned no phones during the 4 months in Hawaii.
Yes.
How is life without phones during the 4 months? And do you actually recommend that we have a phone-free environment sometimes in our home and in our workplace?
How is life without phones? It's quite peaceful. Yeah, we all have this very ambiguous relationship to a smartphone, right? I think we all recognize that. We love it, but we hate it. It would be very different to have life without communication with the outside world. Having daily conversation with your loved ones, the ones you're close to, is very crucial. Of course, you try to, with the people you live with, you try to build a good relationship, but you need that external communication, so that's pretty obvious. It also happens with the astronauts, for example. They are in constant communication with their family and friends, keeps people healthy. So whether it's a phone or internet, in the end, it doesn't really matter that much. And yeah, should we have a phone-free moments? I think you already kind of answered your own question. I mean, it's a rhetorical question, right? I think it would be better if we could sometimes turn the thing off, for sure. What I noticed is, for these kind of projects, I need focus. And a phone is very destructive when you're really thinking deeply with a group of people about solving problems like this. If those phones are constantly ringing, it really does not help. On the contrary, it's really disruptive. So you need to put them aside. I mean, you need to put them aside for 2 reasons. First of all, because it simply blocks it disrupts your concentration. These are scenarios you have to. Thinking about the starships, you really have to project yourself into a future, so it requires a lot of focus. You don't want the phone to disrupt that. Secondly, when you're working with groups of people, like I explained, it's a manner of respect that people are not just constantly checking their phone and are really there with you, with the group in the moment, so obviously. But I think most of these things are well known, so I'm not saying anything new here. But yeah, nice question. I saw a question about biomod. an online question about
yes.
biomod. I don't
Please
know
could
if
you
we can
bring up the question onto the screen?
Yes, this one. This is the part of the goal of the biomod project is to make people think about e-waste. The beautiful thing about the project is that, and what is very engaging in this project is we start with a mountain of e-waste. We always collect a lot of e-waste. We put it together as a kind of a pile of e-waste. And then the first weekend, the first moment we start with the workshop, we give everybody a screwdriver and we're like, go ahead, take it all apart. People love this. Seriously, everybody's like, finally, I can open this thing that has been frustrating me so many times. What is inside? And so they start opening it up, they start understanding, and then by building their own machine, they have a complete different relationship to technology. They feel less threatened. Suddenly they're like, I'm not going to pay $500 to repair my laptop. I'm going to do it myself next time. So this is a very empowering thing. So it might, in this way, because it has a psychological effect, make people buy less new equipment because they know they can repair equipment and it's okay to do that. On the other hand, there is a potential to develop an economy around this. You can actually use those materials, depending on the application that you need. You don't need to upgrade all the time. You can actually combine things and build your own machine as you need it. So yes, this definitely addresses part of the question of electronic waste, for sure.
Next question, please. Can you explain the difference between biomimicry and bio-inspired design?
Yeah, that's a really good question. Thank you for asking that. Biomimicry is basically translating solutions from nature directly into engineering. That's biomimicry. A good example is the wings of an owl. That's a classic example. The edges of the wings of an owl are constructed in such a way that they make no noise. Why don't they make any noise? Because the mice that they eat, they shouldn't hear the owl. Otherwise, the owl would always be unsuccessful in getting the mice. So once they figured out the specific structure of those wings, they applied the same structure on the wings of wind turbines. Because wind turbines were making quite some noise, and with this technology, the wind turbines were much more silent. That's a classic example of biomimicry. Bio-inspired design is a bit more conceptual. The Starship design that I've been presenting today is a typical example of bio-inspired. The Starship is evolving. It's not like directly copying a particular organism or a particular solution from nature. It's more copying a concept from nature, like evolution. And so we call that bio-inspired. So that's the difference between the two.
Next question, please. How would a group co-create if the members have conflicting cultures and beliefs that could potentially affect the output?
Yes, that's a really interesting question. It's also addressed in the paper that I just showed. I'll give you an example of what happened in the Philippines. I'm embracing fusion. You already know it, you already realize this. I like to blend things together. Not because I want to turn the world into the same, but I love combinations of things. Now, we had a bit of a discussion in the team in the Philippines on how to embrace local mythology. Part of the group was like, we need to be very respectful to local mythology and we need to present it as pure as possible, without any kind of mixing and matching. Me, on the other hand, I'm very interested to combine local mythology with, for example, things from game culture, not because I want to be disrespectful, but because I find these new worlds very interesting and because I believe culture is a breathing organism. Culture is not a static thing. This became a very deep ideological discussion in the group that was very difficult to solve. And in the end, I gave in. And I decided that the person that was leading the cultural translation was like, okay, after a lot of conversation, she wanted to hold on to her ideas. And I was like, okay, let's follow your path and your idea. So what this needs is, it needs facilitation. If you co-create, you can't just put people together and be like, co-create, please. That's not going to work. For good decentralized collaboration, you need leadership. It sounds a little like a paradox, like, no, it's decentralized. So yes, but you need, like I said multiple times during my talk, a facilitating leader. The leader is not about his or her ego, his or her position, his or her thought. You are serving the process. That's all you need to do. You're serving the people, you're serving the process, and you're enabling the people in the team. That's your role. So when there is a tension like this, you start up an open conversation and you figure out a solution.
Next question, please. How do you manage the rules to put people in different backgrounds to communicate without any argument?
It's a bit similar to the previous question, of course. The thing is, and this question actually illustrates this, many people have no experience working with other people from different fields, but they have ideas about this. And one of the first things that comes into their mind is, oh my God, that's going to be a huge fight. Actually, you would be surprised how happy people are to work with people from other fields. There's way less conflict than you would expect. And one of the important things is when you put people together like this, different backgrounds, and you want to make them work together, a few rules to get it kick-started. The first one is you have to make sure people don't entrench themselves in their own position. How to explain this? When people come together and they don't know the others, people will very quickly fall back to their important position in life to establish their position in the group. I'm the director of this. I'm an engineer specialized in this. And everybody starts to put themselves in a very important position. You have to avoid this. Don't give people time to do this. That's a really good trick. So don't talk too much. Start working straight away. Second trick, throw the whole group into an exercise everybody feels uncomfortable about. Very good trick. It always works. Take everybody out of their comfort zone. What happens is if you take everybody out of the comfort zone, nobody can be the specialists. Nobody can dominate. And so what happens in Biomod with the recycling of the computers is the first exercise we do. 99% of the people have never recycled a computer. So everybody's like, oh my God, what is this? I don't know how to do this. And this establishes a base culture within the group, psychologically, that you can take along during the whole process. The first hours are really important in establishing such a group.
Next question, please. How to fry vegetables under the circumstances of no gravity in the outer space? Great question.
Well, I think that's interesting. There is no device yet to fry vegetables in no gravity, but I'm sure there must be a possibility. So once we move out into space, there is a business opportunity there. So please go ahead, start a startup, frying vegetables in space. Sure.
Next, please. Do you think Biomod can help solve the problem of...
We had that.
Yeah, we
had that question.
Are there any more questions from the floor while we're waiting? Here at the front.
At the front? Oh, yes.
Okay. Thanks, Angelo. That was a great presentation. I want to know how you can steer the asteroid.
Yes, good question. So the goal of the idea of using the asteroid is first you would rendezvous with the asteroid. That's a typical strategy in space exploration. Rendezvous means there is something moving in space, and then you take the same speed next to it. So it's much easier to jump on and off it. That's something they practiced very early in the space program. So you would do the same with the space asteroid. And then you would place booster thrusters on the outside of the asteroid, and then slowly, using the thrusters, redirect it. So you would basically already use the kinetic energy of the asteroid, but you would redirect it using thrusters on different positions of the asteroid. That's basic, some basic aerospace dynamics you can use there. Okay?
Next question, please. How scientifically accurate is a spore drive, or what the Star Trek's USS Discovery uses to travel to another places through the mycelial network?
Yeah, I'm a little disappointed about this. Not about the question, but about the whole concept of the spore drive. It doesn't resonate with me. I find it hard to get into it. It sounded like an interesting concept, but not so much, I'm afraid. Let's say it's poetic, and that's pretty much what it is.
And the last question from the floor, perhaps.
Oh, we have him.
Up at the front on the right, please.
Hello.
Oops, I think the microphone is off, right?
Hello. Okay.
Yeah, okay.
Talking about serendipity, how do you manage yourself to find such great opportunities along your career path?
I move out of my studio all the time. I travel a lot. I've always liked to travel a lot. And I very much work with the power of meeting people and then trusting my intuition with the people that I meet to set up something or to explore a collaboration. Sometimes it doesn't lead too much, but sometimes it really leads to quite interesting things. It's all about being out there. I'm not talking about kind of aggressively promoting yourself all the time. It gets tiring too. But it's more like trusting your intuition and opportunities and people. And I'm afraid there is no real manual for this. But definitely going out, leaving your comfort zone, going to different places, meeting people is a good first step. And sometimes taking risks, just trying something out and not really knowing whether it will lead to something. Another thing is, time's up, just to finish. When you're developing projects one after the other, once you have a project that is working well, sometimes people abandon it after some time because they get tired of it. Sometimes it might be interesting to keep a certain line in your work. Like the Biomod project, multiple times I thought, I'm going to stop it. I'm done, I've had enough. But somehow it keeps on evolving, and I'm like, maybe it's meant to keep evolving, so I'll keep it as part of my life. So if you have a few directions that are strong in your life, you can allow yourself to experiment and to fail or to explore things that might not be as successful, but it will enrich your capacities, of course. All right?